follow up with our analysis of using NMR to examine biomolecules like amino acids, I would like to talk about how we can now use something referred to as D2O, which is a water molecule, but instead of protons, it has deuterium atoms, which is just a proton, but with a neutron. And the thing that's cool about D2O is that it doesn't show up on high field NMR. So the traditional NMR techniques that we're using. And the reason it is helpful to us is because we can now use D2O, specifically the exchange of deuterium atoms with a molecule like valine, to determine how acidic a proton is. And so, as we'll recall from general chemistry and some organic chemistry courses, when a molecule is present in solution, like an aqueous solution, there's going to be some protons floating around here and there. And if we introduce deuterium, there's going to be some deuterium atoms as well. And these deuterium atoms will exchange on a molecule. And if we wanted to determine like what kind of protons on valine are acidic, we can do that by adding a few drops of deuterium onto valine, or into our solution. And if we create a high enough molar ratio of water to D2O, what we'll find is that we're going to start seeing our peaks changing and evolving over time. And so what I mean by that is if we had some kind of if we look at peak B, for instance, this amino group on our valine, these amino protons will exchange with solution. And so if you had some deuterium atom come in here and swap out with this amine, what will happen is this signal intensity, as we'll recall, the peak area on our NMR spectra is proportional to the number of protons that are present. And so if we're taking off protons and substituting them with deuterium, the area will decrease over time. And so if we plot a function t on our x-axis and peak area of peak B, for instance, what we would find is that as we continually run our NMR spectra again and again over a certain time interval, we're going to find our peak area decreasing. That's not drawn too well, but we'll see something like this. And based on this curve, if we fit some kind of function to it, it would tell us the kinetic parameters of our protons on this amine. And what we would also find is that if we examined peak A, for instance, peak A area versus time with D2O in solution, nothing's going to happen because these methyl groups do not exchange protons readily. And so it is useful information for us to be able to determine when we're interested in this kinds of stuff. If we examine how peak E evolves with time, if we introduce D2O, we find that it would increase even faster than that of B, because this is a carboxylic acid. It's got conjugate, it's got a very stable conjugate base because of resonance structures, and therefore what we would find is that proton will very readily exchange with a deuterium in our solution. And so it is helpful for us to begin to look at pKa values, for instance, as well as other kinetic parameters that help us deduce information from these biomolecules. And so I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.